I want to do today is run through the main points of the proof that diptychs exist. So you probably remember, Miles and I, we often work out an example and try to say that if you understand that example, then basically you understand everything. And there's a sort of small amount of dishonesty in that. That it's true there's lots and lots of things in the examples, but there's 2 or 3 points which the examples don't cover. And it's those 2 or 3 points I want to touch on today. I want to do them sort of in the wrong order because it's convenient to do them in the wrong order. You know, do the hard part first while we're awake and all that. Let me just, I'll give a sort of beginning hint of what I want to do. This sort of uses all the notation. So remember VAB. And this has a picture that looks like this. I'm not going to need this full generality to explain the main points of the proof, but just for the moment I'll stick to it. So this has various variables up the side up to xk, and if you remember there are tags with these, a1, a2 and so on. And on the other side there's y's with tags b1 and so on up to yl. And there was a little tag here called A, and a little tag here B, and these deformation variables A and B. And the calculation Miles did, which is kind of critical, is the starting point is to work out, in terms of these 4 variables, what are all the other variables. So in other words, this was to write, when he says, this defines a toric variety, and he says it defines a toric variety which has cone in Z4. Well, you know, I really mean tensor cube, of course. But with the basis chosen to be xk, yl, a, and b. I'm not going to do this calculation in full, but let me just remind you exactly how this one works. This is a very easy one. So, of course, this cone means the cone generated by x0 all the way up to xk, y0 all the way up to yl, and a and b. And the thing that we know is these little tag equations down here. So if we've got a tag here, which is a, k minus 1, then where I have a little tag equation at the top here, which was xk minus 1 times yl is equal to xk to the a, capital A. That's one of these tag equations, just these things we're giving ourselves right to start with. And that was how we deform this corner. But rearranging it gives that xk minus 1 is, I'm going to divide through by the yl. xk a, capital A, yl minus 1 is now expressed in terms of the basis that I want it to be expressed in. Is expressed in the basis. This basis here. So this is the basis. And then you can continue down the x side by writing xk minus 2 is, well, we had a tag which was, if I just remember that, xk minus 2 times xk is xk minus 1 to the ak minus 1. And then dividing through by xk gives me xk minus 1, ak minus 1, xk to the minus 1. And I can plug in my value for xk minus 1 into that to solve this. So let me just do that. I'm not going to do many of these. Xk to a minus 1, and then a yl minus 1, a to k minus 1, and so on. And the thing that you see here is that in this basis, the power of a here is increasing. It's gone from a single power of a to a ak minus 1th power of a, and I'm imagining, let me imagine for now that these are at least 2. So the thought here as j decreases, from k down to 0, the power of A appearing in the expression for xj, so this is the same j, increases. In other words, if you consider these as little vectors in Z4 and look at their A component, then the A component is increasing as you go down this rectangle. Yeah, that's right. And similarly, for the B coefficient in the yj's. So written in coordinates, this is very heavy in A's and B's at the bottom and very light in A's and B's at the top. And you could do the same for VLM. You can do the same for VLM. Of course, VLM works the other way around. VLM works from the bottom up. So in that case, powers of L and M increase as you climb up the rectangle. Okay, that's fine, and that's sort of basically the easy thing. The slightly more fiddly thing that I want to do is I want to not use this basis. This basis depends on xk and xl for VAB, and in VLM it's a different basis altogether because it's using x0 and y0. So I want to use a basis which is the same for both of them. So much better, not just better, much better, is consider Z4 sitting inside rational vector space. I just have to be a little bit careful here. Rational vector space with basis L, M, A, and B. So this is good. It's not favouring VAB or VLM. In the end, I want to use both of these kind of facts at the same time, and I don't want to use it just on VAB or VLM. So this is a kind of just a remark about why you might think this is good. This basis does not favour VAB or VLM. We call it the impartial basis. It doesn't have a favourite. We call it the impartial basis. So that's exactly the phrase that we use in the paper. So in other words, what I'd like to do here, I've expressed all the x's and in principle all the y's in coordinates in a given basis, and I want to do that again, but in that basis. And it's just slightly not as easy. But let me give you an example. So that's a completely general thing. I'll show you one or two examples, and then we'll be able to understand the completely general answer in one go. So this looks slightly different, and you'll see why I've written rationals. So, for example, let me take the smallest possible diptychs, smallest possible pairs of long rectangles. So I'm just going to have x0, x1, y0, and y1. And I want one for AB and one for LM. So here's going to be an AB. So this is for VAB. And this is for VLM. I can say, what do I have to do? I have to put some tags on here, which I'm just choosing to be 2 and 0. And if you write out the equations. There's a 0 minus 2 on the bottom. And then here I'm going to do 3, 0, the bottom, with these L and M sitting there. So in other words, what I have in mind here is that x1, y0 is y1 to the nothing times b, whereas here I have in mind that x1, y0 is x1, y0 is bottom left-hand corner. That's x0 cubed L. So the equation is slightly different in the two toric varieties there. And here I have in mind that x0, y1 is x1. x0, y1 is x1 squared A, whereas here x0, y1 is x0, y1 is y0 for nothing times n. So that's so far so good. And I want to use these equations to write down the x's and the y's in terms of a, b, l, m. And I don't care if I pick up rational numbers. It's sort of inevitable. So let me look at this equation here. So x1, y0 has the same homogeneity as b with respect to this, the torus. So x0, what did I say? I said x1. x1, y0, let me write this, twiddles, b, and I'll say what I mean here. I'm going to use this notation a lot. Of course, in this toric variety, they're equal. But here I just mean they have the same weights, the same homogeneity with respect to the torus. So, i.e., these monomials have same degree of homogeneity. Homogeneity with respect to the torus, the big torus. So as I say, of course they're equal in VAB, but let me not say that. So maybe that's not the equation I wanted. Let me very good, very good. So I have this. x1, y0 has the same homogeneity as b from VAB, but it also has the same homogeneity as x cubed L from VLM. So you can see why I'm avoiding the equals here, because I'm dealing on two different varieties at the moment. I don't have the big sixfold which combines them. So x0 cubed has the same homogeneity as b over L. Is that right? Yes, that looks good. So in other words, in coordinates, I want to write this now in coordinates of LMAB. So in LMAB coordinates, x0 is, and now it's going to be a vector of rational numbers, well, the A entry is 0, the B entry is plus 1/3. This is very good. This is very good. My notes are wrong, but what's on the board is right. So the L and I'm sorry, I've gone this the wrong way. LMAB. L is -1, but it's got a cube, so it's -1/3. M is nothing. A is nothing. And B is 1/3. So I'm thinking of that as being an element of q to the 4. If I take 3 times it, I get b minus L, which is exactly what I wrote. So let me just remind you, these coordinates are L, M, A, B in that order. Simple. If you're comfortable with this, then you've won. So I want to do everybody else as well. X1 squared A has the same homogeneity as M because they're both equal to the same monomial in their respective varieties. So X1 squared A has the same homogeneity as M. So in the same coordinates, X1 is X1 squared is M over A. So it's got no L's. It's got half an M. It's got minus half an A, and it's got no B's. Well, I'd like to do the others. I wanted to just write them down, but my notes are letting me down now. So, who's Y0? Oh, I own X1. I know B is one of the coordinates, so I can get Y0 from this. So Y0 has the same homogeneity as B divided by X1. In other words, it's 0, 0, 0, 1 minus X1. So that's 0 minus a half, half, 1. And Y1, Y1 is the same as same degree as M over X0. So it's 0, 1, 0, 0 minus X0, which is 1/3, 1, 0 minus 1/3. That's very good. So that's the calculation. That's a slightly different calculation from the original one in monomials, which we used to build the toric variety in the first place. We still need both of them. The first one to build the toric variety, but this is kind of the key point in the proof. So if you've got the notes, compare this with proposition 4.1 and example 4.5 in the notes. I'll write this down as well in the paper. I copied down the bit of this. This says, for example, if K is even, that's to say if there's x naught up to an even number of x to the even subscript, so there's odd numbers of x's, then xk is looks like this. There's some numbers there, gamma and delta, and then minus 1 over d, 0. Xk minus 1 is some numbers alpha, beta, and then 0, 1 over e. And if I come all the way down to x1 and x0, I see 0, 1 over e, alpha, beta, and minus 1 over d, 0, gamma, delta, assuming that the tags on the left-hand side on the xi are, I've got to get this right, d, e, even number of times. And something similar for the y's. For the yj. So this calculation in the baby case was very easy, and you can imagine how to do this calculation in exactly the same way, given that these are the tags. But here's a little remark. This is where I'm doing something in the wrong order. It looks a little bit like I'm just taking a special case of one possible outline of the tags. But in fact, this is one of only 2 general cases. And that's what I want to prove next lecture. So here's a sort of big remark. This DE structure. Hi. 3 here. I've drawn them upside down, of course. That's right. Thanks. But here, this example here, k is odd. You're exactly right. Yeah, no, you're exactly right. It's there's a different picture for k odd, but basically the same. This DE structure for the tags is the result of a classification statement. So the proof, and everything I'm showing you about the proof is assuming that we already know this classification. So I'll show you how to do the classification later, but there are 1 or 2 key points where we use the fact that we know that those were the tags. This is one of them. Use a classification statement, I'll prove this later. Very good. It's a relatively easy thing to do once you've thought of doing it. So the thing to notice about this is that this idea that was coming from the original toric tags, the A's and the B's increasing, still happens here. So you can see, let me just remind us which are the coordinates. This is the L coordinate, the M coordinate, the A and the B. So as we climb up from the bottom of the rectangle, the L's and the M's increase. Whereas as we come down from the top, it's the A's and the B's that increase. So that was obvious in the original toric calculation, and here it's just a result of this calculation, a result of being able to start with this little corner here. So let me carry out the kind of full proof on a big worked example. So we can see the places where the examples don't quite fill in the proof, but then fill in the proof at that point. So I want to start with this. So this isn't quite the same as the example that Miles did. It's just a little bit smaller. 21AB. So that's VAB I'm writing here. 0 minus 1. Just again, to notice here we've got this 2, 3, 2 alternating behavior, which is a kind of DE, DE behavior. So again, this example, I'm writing it not out of the blue, I'm writing it because I know the classification. And the other way up, well, the torso here is the same, and it's just the ends that change, so this is going to be 3, 2, 3. So again, that DE behavior. 1, and then 0 minus 2, and LM. So this is VAB, this is VLM. So maybe I can just run the entire proof, which is in several steps. So step 1, understand these monomials on VAB, the original calculation. So write the monomials of VAB in basis the toric basis that suits VAB, which is x3, y3, a and b. So again, I'm retreating from the favoured basis. So x2 is x3 squared ay3 inverse. Let me just check 1 or 2 of these before I write the answer. So in other words, it should be x2 y3 is x3 squared a. Yes, that's good. And then charging down, x1 is x3 to the 5 ay inverse, y3 inverse to the cubed, and x0 is x3 to the 8, a y3 inverse to the 5. That's good. And the y's, y2 is y3 b x3 inverse. And let me just check that. Y2 times x3 is y3 times b. That's right, good. Then y1 is y3 squared times bx3 inverse to 3. And y0 is y3 cubed bx3 inverse to the 5. So this will give us the equations at the bottom of VAB. This determines the equations of the VAB. In particular, at the bottom I have x1, y0. If I look at x1 times y0 there, the y3's cancel, the x3's cancel, so it looks like a cubed b to 5, and x0, y1. X0, y1, well, things don't quite cancel, but if I put in a x1, that gobbles up the excess. So this is x1a squared b cubed. That's the kind of thing Miles was doing last time. Step 2, maybe this is part of step 1, but think of it separately. I want to just log the projection sequence of VAB. So I can eliminate variables from VAB one at a time, and I want to record that. So record projection sequence VAB. So in order, we can eliminate well, the first one to go is y3 because it's got a 1 here. So y3 appears linearly in the equations, and here it's times b, which multiplies b. So y3 appears linearly in all the other equations, of course, because it's just multiplying variables that are not its neighbours. But the place it might not appear linearly is in the tag equation at y3. But this one says it does appear linearly and its partner is b. Now, of course, this we've seen before. Of course, what we're going to do is cross him out, and that produces these two by 1 each. And so there's a new guy here who is tagged by 1. So the next person to be eliminated is x3, which multiplies ab, and so on. So I'll just record more, y2, which multiplies ab squared, x2, which multiplies a squared b cubed. So in other words, these here are telling you what the ideal of the unprojection divisor was if you wanted to recreate VAB from its projected varieties. So these multiplication partners describe an unprojection ideal. On VAB, which we'll see this later. We could write it all out now, but we'll be coming across it later in any case. So I need to repeat the whole thing for VLM, which I'm not going to do, but if you like, this pair of wrong rectangles are the input. I've completely analysed VAB, and that's the one I'm going to really rely on. I'm going to use this projection sequence of VAB to build the final sixfold, but I need to know the data for VLM, so 3 is record similar data for VLM. We kind of tend to do it for fun anyway. So let me assume that's done. And then 4 is I'm going to start the building. So this is, for start building VABLM from the bottom up. So that's, we define ourselves as V0 is this complete intersection x1, y0 is equal to, as explained, we're just going to take the equation on the right-hand side for VAB and add to it the same equation for VLM, which I haven't written down, but you can see actually what is x1, y0 over here. x1, y0 is x0 cubed times L. So I just add that on. x0 cubed times L, and x0, y1 is x1 a squared b cubed plus y0m. And that's in, how many variables do I have? 8 variables, so in the C8 with variables x1, x0, x1, y0, y1, a, b, l, m. So in other words, I've given myself a little equation down here. And one at a time, I want to reintroduce the variables, pulling these equations up with me. So I need an unprojection divisor, so sitting inside here is this unprojection divisor d0, which is going to be defined by x0 is x1 is a squared b cubed is 0 in the same space. Well, let me just check what's going on here. We're in a C8, and this is, so a sixfold, it's a complete intersection of two things, so this is sixfold, so that makes sense. Again, we're in C8, and here's 3 equations which are clearly independent, so this is a fivefold. It's a kind of, it's a, as a divisor, it's a, you might want to think of it as being twice x0 equals, I beg your pardon. That's not an x1 though, that's a y0. Twice x0 is y0 is a, plus 3 times x0 is y0 is b, is 0. Anyway, it's 3 equations in this complete intersection inside C8, so whatever else it is, it's 5-dimensional. So D certainly is D is the right dimension to be a divisor on V, and this is going to be the key point. Why is that true? Why is D0 inside V? Well, it's kind of obvious, right? I mean, if I set V is equal 0, I hope it's going to be kind of obvious. If I set x0 is 0, that removes this term and this term. If I set y0 is 0, that removes these two. And a squared b cubed is a factor of both of these, so both of those vanish, so that's obvious. We can just see that visibly. So let me not put a question mark there, and let's just say visibly that's true. So we've started. And so step 5, and this is the bit where the proof actually happens now. Everything so far we've kind of seen. Step 5 is serial and projection. I want to reintroduce these variables that we eliminated in VAB back in the reverse order. So reintroduce the variables x, well, let me write down the order. From the bottom, it's x2, y2, x3, y3. So in that order, using unprojection. Unprojection is going to need a divisor, that's what we've got here. So each stage we're going to have to cook up a divisor. And so let me just say in advance, but we'll see as it happens. We'll use the defining equations of the corresponding unprojection divisor on VAB unprojection divisor of VAB to define the divisor here, the unprojection divisor here. Okay, these can go here. I'll show you this exercise, this jigsaw puzzle with Pfaffins. It's not absolutely necessary for this, but I'd like to do it again so that we can see how things work at first. So, repeat the Pfaffin jigsaw puzzle. From last week. So in other words, we've got two equations, and I need to add a projection divisor. It's going to be Gorenstein code. I mentioned 3, so I reasonably guess that it's 5 by 5 Pfaffins, and I can. Hi.
And that's the T0 is always like x0, y0, some a power.
That's right. That's right. This is. I see what you're saying. So this is, of course, this is just a particular case, but this is completely general. I mean, the powers here will be slightly different. These powers are these things I was calling alpha, beta, gamma, delta in the, when I wrote out the coordinates of VLM. They're determined by the continued fraction expansions of the original tent. But that's right. We just write down exactly the same thing, take the VAB side, the VLM side, and just start with that in every single example. We've never done anything else. This jigsaw puzzle is going to give us a few more of the equations, but it's, and the first step, it's going to give us all of them, but that's not going to be true all the time. Let me write down this jigsaw. x1, x0, so if you remember, this is going to be a 5 by 5 matrix. I'm omitting the diagonal. y0, y1. And then I have to mount these equations into this. So this first Pfaffin here, which is x1, y0, is that times that minus that times that. We've got to pick up this equation here. x1, y0 is, well, x0 is going to be x0 squared L times x0. And then this product here has to be a cubed b5 somehow, so I have to divide those up. Well, the way to do it is this. Work out the other equation, and then this product here now has to be x1a squared b cubed, so it's certainly a solution if I put the greatest common factor there, ab squared there and x1 there. That's certainly one way of making those two Pfaffins. I could, of course, put something smaller there, but I choose not to. And then the unprojection is just by putting a new variable, which was x2 indeed it was, x2 up there. So take the 5 by 5, take the maximal 4x4 Pfaffians of this matrix. These give the equations for V1, and I'll write them out. So V1 is, well, I want to keep the two equations V0 and the three Pfaffians that I can see here, which are x0, x2 is x0, x2 is x1 squared. That's good. That was a tag equation plus a squared, ab squared m. X2 y0 is y1 ab squared. So x2 y0 is y1 ab squared, x0 squared x1l, x0 squared x1l, and the missing one is x1 y1. This long one by crossing out the third row and column is x2 a squared b cubed plus x0 squared lm. So the signs are a little bit incorrect. I think I can't get these exactly right, but if we do something like that, then probably they come out right. In the paper we get them right. Okay, well we need to continue, so I need an unprojection divisor in here. We take away this apology for the signs, it's not the point. Now, unfortunately I've crossed out the multiplication partners in the VAB. Certainly what I want is x0 is x1 is y0 is 0, but then I want this new new term here. This is the partner of y2. Partner of y2 in VAB. In other words, those equations define the unprojection divisor in VAB. I'm just using them to define the unprojection divisor in V1. Right. In other words, I'm simply using the unprojection divisor equations, unprojection divisor equations of VAB for V1. No reason at all why they should work. Let's check again the dimensions. So that's a sixfold. This is four equations. We've added one new variable, so we're in C9 now. This is four equations in C9. They're obviously independent, so this is a fivefold. And then again, the question is, why is D1 actually inside V1? Well, again, we have to run through these. Of course, the previous lot of equations are satisfied, because already if we said x0, y0, and something bigger than ab squared 0, we'd already won. Remember, the a squared b cubed is now strictly decreased. So these two equations of V0, these two equations up here are fine. So we have to check these, but again, you can just check them. You can see this. You can see from the equations. Fine. So I continue. So far nothing. So far there's no proof required. We can just see everything. So V2 is then the five equations of V1 plus some unprojection equations. Well, again, I've got to do the little jigsaw. I'm going to take, let me just write it down. I'm taking x2, x1, x0, y1, and y2. So this is include y2, but exclude y0. Well, y0 is the first projection from VLM. And what goes in here is x1 there, m ab squared, x2 ab, and x0 lm. That's just the same exercise. So of course I can quickly write these down. x1 y2 is x2 squared ab plus x0 lm squared. x2 y1 is y2 ab squared plus x0 x1 lm, and x0 y2 is x1 x2 ab plus y1 m. But I haven't deformed all the equations yet. I haven't yet done anything with y0 y2 is y1 squared. I have no idea what to write there. This faffing game has not given it. I mean, maybe I don't care. There's certainly variety there. There's some projection theorem says there's a variety there. That's what Miles explained. I can still write down D2, because we've just got a rule for this, which is just write down the basis that you're using on V0. So let me, oh sorry, on VAB. So let me write this down. It's that x0, x1, y0, y1, and now AB are 0. So again, the dimensions are right for D2 to be a divisor inside V2. But now, I really have no idea at all why that's contained inside, why D2 is contained inside V2. Because I can't look at the equations because I don't own the equations. So I have two methods at this stage. So let me just set this as an exercise, which maybe I'll do it over the break and we can compare notes. So exercise, could use syzygies to determine exactly what this equation is and check that, to determine the deformed y0, y2 is y1 squared plus extra terms equation. And if you did that, then you could check that indeed it would be true that D2 is in V2 for the same reason. So this would give that D2 is in V2. But I want to do something much better. So finally I get to kind of main point of the proof.
We want to treat this as complete intersections.
That's exactly right. You're absolutely right. This is in C10, so this is in codimension 4, and it's certainly got these 9 equations, one of which I don't know. So the thing that I'm going to do is, I'm not actually going to calculate this. I mean, I'll do this exercise later if we like, or maybe you can do the exercise. But instead of working out what this equation is going to be, I'm going to say, well, these equations are all homogeneous with respect to the torus, and so absolutely any monomial that I could put here at all, which has the same homogeneity as y0, y2, is divisible by one of these, and therefore is in the ideal. So I don't calculate the y0, y2 is y1 squared plus extra terms equation. Instead, I show that any monomial m appearing on the right-hand side right-hand side of this equation must lie in the ideal of D2. And I'm just going to consider all possible m's. In general, let me be slightly stupid, m is a monomial in the variables that we own. Well, we've got a bunch of variables here, 10 variables, so m is going to be x0 to the something, x1 to the something, x2 to the something, and so on. y0 to something, y1 to something, y2 to something. We've gone this far, so a, b, l, and m, all to some powers, and I need to check every single case. Of course, if this x0 factor is appearing non-trivially, so if that power there is positive, then m, whatever the rest is, m is in this ideal because x0 is in the ideal of reduced. So if x0 appears to a positive power, then m is in the ideal of D2. The same goes for x1, y0, and y1. Similarly, x1, y0, y1. So consider m of this form, which doesn't have any x0s, x1s, y0s, or y1s in it. So x2 to the psi, y2 to the eta, a to the alpha, b to the beta, L to the lambda, and M to the mu. These alphas and betas and so on, they're just new integers that have nothing to do with previous alphas and betas. I'll try and keep this ideal of D2 for a moment on the board. Is there any chance at all that that could be in the ideal of D2? Well, the only thing that could make it work is if it's divisible by this monomial here. So m is in the ideal of D2 if AB divides m. And so that's what I need to show. So there's just 2 or 3 little reductions. First of all, this equation is, this monomial is meant to be appearing in this equation here. In other words, it's meant to be have the same homogeneity as y0, y2. So I claim that eta is 0. In other words, y2 certainly doesn't appear here. Otherwise, y0, y2 is equivalent to m. In other words, has the same degrees with respect to the torus as m. So y0 has the same degrees as x2 to the psi, y2 to the eta minus 1, a, b, l, m to their powers, alpha, beta, lambda, mu. Well, that's not on the face of it, obviously false, obviously a problem, but expressed now in the impartial basis of LMAB coordinates, this would say that y0 was equal to some entries, some 4 entries, which was a sum of other variables. In other words, all 4 entries satisfy these equations. So in particular, the AB coefficients satisfy this equation. In other words, y0 is homogeneous is homogeneously equivalent to another monomial on VAB, but that's just not true. But this on VAB, y0 is part of a minimal basis. Minimal basis, so it's not T equivariant to anybody else. Fair enough. I can lose these equations. So that's great. So in other words, I've got this monomial here. The only thing that could possibly cause a problem now is a monomial of that form. I've got to show that that's divisible by AB just by its homogeneity. So recall that, so this is part 2 of this exercise. Recall x1, y2 is equivalent to x2 squared AB. Well, that's just part of one of the equations we had, with an equal sign. That's one of the equations of VAB. So if m is, let me just write this down again, it's x2 psi AB lm to the alpha, beta, lambda, mu. It satisfies y0, y2 is equivalent to m. In other words, if m could possibly appear on the right-hand side of the y0, y2 equation, then dividing gives, we can divide this equation by that equation, gives y0, which will we round on to it? Yes, y0, y2 divided by x1, y2, dividing this equation by that equation, is equivalent to m divided by x2 squared AB. And I want this to give a contradiction very quickly. This is, on the left-hand side, it's y0 over x1, the y2's cancel. Whereas on the right-hand side, this is x2 to the psi minus 2 times a b lm to their powers alpha, beta, lambda, mu, divided by AB. Right. Okay, so there's 2 steps. I'm going to use those increasing and decreasing results that are very easy right at the beginning in the impartial basis. So in the impartial basis, y0 is down at the bottom of the long rectangle, so x1's a little bit further up. So in other words, the lm, let me try and get this right. Let's think about it. Can we have a little sort of brain thing going on over here? Here's the AB. Here's the LM. Just in the old wrong basis, it's clear that the ABs are growing as you go down, as the LMs are growing as you go up. And that's also true in the impartial basis. In other words, x1 has bigger LM components than y0. So in the impartial basis, the LM components on the left-hand side are negative. There's just 1 or 2 cases where that could actually be equals to 0, but let me ignore all the boundary cases for now, just to do the main case. Well, if they're negative on the left, they've got to be negative on the right. But you look on the right, in the numerator here is some part of monomials, so that's positive. So there's no negative LMs here, so the negative LMs had better come from x2. In other words, that power had better be negative. So xi minus 2 had better be negative. So rewrite as, I'm just going to multiply across, right? I don't want that sticking in the denominator. So y naught, x2 to the 2 minus xi, which is now positive, over x1 is equivalent to this ABLM, alpha beta lambda mu powers, divided by AB. So in the second part of this, I'm going to consider the impartial basis again, but now consider the AB coefficients. So in the impartial basis, the AB coordinates, components, let me think, the ABs grow as you go down. It grows as you go down. I very much want this to be positive. Oh, that's very good, isn't it? Y0 is below x1, so the y0s are going to be, the y0 AB coefficients are bigger than the x1 ones. The x2s are even more positive, so the ABs on the left-hand side are positive. So they're also positive on the right-hand side. That's to say, AB divides A to the alpha beta beta. In other words, AB divides M. So M is in the ideal of D2. Well, we've lost the equations now. But what we've found here is that anyone who could appear in the equation y0, y2 also lies in D2. So the whole equation y0, y2 minus y1 squared minus anything else is in the ideal of D2. And so, just dot the things. The ideal of V2 is inside the ideal of D2. So D2 is in V2. Very good. So I've lost the equations, but I never did work out what that final equation was for y0, y2, but I get the inclusion of ideals the way I want it anyway. And that's how the general proof works. Let me show you a more general case, just so we're not stuck in this example the whole time. More generally, there's one or two cases that get a little bit trickier, but let me show you an easiest case. Inductively, we've reached a V nu with variables xi, yj at the top, and various tags and so on. And from VAB, we have that xi yj minus 1 is equivalent to yj beta nu b nu. So here there are some tags, alpha nu, beta nu, and there's these a nus and b nus, which are some monomials in a's and b's. Those partner monomials that we recorded right at the beginning. So there's a tag equation in the corner there, and there's a tag equation in the corner here, which is xi minus 1yj is xi to the alpha nu, a nu. So what is the equation? Well, I've worked out these equations here, across the top here, xi minus 1. What's the equation, for instance, from xi down to yj minus 2? It might be one of the Pfaffians, but if I carry on a little bit further, it's certainly not anymore. So xi yj minus 2, what's on the right-hand side of that? Well, I don't know, but I can still check that it's in d nu. I don't know, but I can check it lies in d nu, which is, and now I need to write down the ideal from AOB, which is all the variables down lower than I minus 1, all the variables lower than j minus 1. So x0 is to xi minus 2 xi minus what is y0 is yj minus 1 is, and then some monomial h nu here is 0. H nu is the GCD of these two, so the smaller of those two. Again, suppose not. So the proof is similar. So consider m equals x I to the psi yj to the eta a to the alpha beta L lambda m mu, not in ID, with m equivalent to xi yj minus 2. So again, the first case, if this xi yj minus 2 is equivalent to this monomial, then there better be no xi's in there, otherwise I get a relation for yj minus 2, which doesn't hold on either of the toric varieties. So psi equals 0, as before. And now I'm going to take the relation here that I have and divide it by one of these. What looks quite good here? Dividing by the first one would cancel off the xi's. So divide xi yj minus 2 twiddles m by one of the model equations. These two model equations, which I already got for free from VAB. So I'll do this one, xi yj minus 2 divided by xi yj minus 1 is, ignore the xi part because we just killed that, ABLM to their various powers divided by yj b nu b nu. And over on this side it's yj minus 2 over yj minus 1, whereas on this side it's yj to the eta minus beta nu times again ABLM for beta lambda nu over b nu. It's enough to get divisibility by b nu. One of these will actually divide the other, so this I'm not worrying too much about who H is. So I want to understand the coefficients on the left-hand side. So the LM coefficients, so I just have to think about this again. The LMs are bigger, higher up the rectangle. So yj minus 1 has bigger LM coefficients than yj minus 2 because it's higher up the rectangle. So LM coefficients on the left-hand side are negative. So eta minus beta nu is negative. So if I, let me just be kind of clumsy, and multiply that across to be y to the beta nu minus eta, sorry, that's pretty awful, isn't it? But I'm just multiplying that across to keep everything positive that I know. So B, what are the AB coefficients? So this is yj. The AB coefficients are bigger at the bottom than they are at the top. Good. Here I've got someone who's lower down. Which way around are we going? We start at 0 and we work out fine. This has bigger AB coefficients than this, and this is already positive. So the AB coefficients on the new left-hand side are positive. So also on the right. B nu divides ABLM, alpha, beta, lambda, nu. So B nu divides M. And M is in the ideal of D2. The way I said that, that's come out as a contradiction, hasn't it? But, so whichever way you like to play it. I'd just like to make one little remark here. I keep talking about people being higher up or lower down in the rectangles. It's not really that. It's how they project or unproject in AB and LM. So the statement about increasing and decreasing coefficients is about their projection order in VAB and VLM, and not strictly their height. Now, of course, if we're just in one side, we're just looking at y's, then you can't, as long as those tags are at least 2, you don't project away lower y's before you project higher ones. So the thing about height there is exactly right. But this is one of the only 2 or 3 little points that just have to be understood to make the proof precisely right. But that's a very small point. It's just a few lines of remark in the paper, I think. The main point that's missing is this classification of pairs along rectangles in the first place, because that's what we use to build the big grid of impartial coordinates, and that's the thing that we're using all the time here in just exactly the way you see. The proof is basically this easy with 1 or 2 slightly more fiddly bits, but we just need that classification, and that's what I'd like to do.